So today we will take up this analysis of rigid plane frame by stiffness method. I have taken a problem here. A rigid portal frame subjected to UDL on column as well as beam. Now I have taken both ends fixed here. Earlier we worked with the problem by flexibility method, making one of the supports hinge. Now I am taking both fixed. So let us analyze this. So as usual, the same 7 steps to be followed. The first step, you have to identify the element coordinates. So there are 3 elements here, AB, BC and CD. So we are choosing the moments at the ends of each of these members as the unknown. 2 forces we select as the moments at the ends as the unknown. So at AB, the 2 moments and the coordinate direction is clockwise positive. So this is first coordinate, second coordinate in member AB. Likewise in member BC also 2 moments, 3 and 4 coordinates, and in member CD again 2 end moments are chosen as the 2 coordinates. So totally 6 coordinates. So we have to determine the moments at these ends of the members. So that is, we have to determine PM1, PM2, PM3, PM4, PM5 and PM6 corresponding to these 6 coordinates. So it is a 6 by 1 matrix. So that is what first step. You have to identify what are the internal member forces to be determined. They are selecting the end moments as the end forces, so that I have indicated by coordinates. Then you can generate PMS, that is, assuming the ends to be fixed for whatever the load is there on the members. Due to that, the fixed end moments to be determined. So here, first we can take the ends A and B to be fixed. So you have UDL, find the fixed end moment. Here, fixed end moment will be like this because applied load is like this. Here, it is clockwise. So this moment is WA squared by 12, that is 25 into 6 squared by 12, that is 75. Here also it is 75. Corresponding to coordinates 1 and 2, the given fixed end moments due to the load, they are 75 and 75. Similarly, on BC, assuming the ends B and C to be fixed, you have UDL of 50 kilonewton per meter or 25 kilonewton per meter. Here also, you are getting the end moments corresponding to the coordinates 3 and 4, and that is also equal to 75 because that load is also 25. So moment will be 25 into span squared by 12, that is 6 squared by 12, that is 75. So then on CD, there is no member load, there is no load, so naturally there are no moments. So therefore, the PMF matrix, that is the fixed end moment matrix corresponding to these element coordinates or corresponding to 1, it is minus 75 because it is anti-clockwise. So here it is 75, corresponding to 2, corresponding to 3 it is again minus 75, corresponds to 4 it is plus 75, and corresponds to 5 and 6 it is 0. This PMF matrix is also 6 by 1. Then the second step, we have to find out the kinematic independency. That is kinematic independency. Here it is 3, assuming members to be axially rigid. Assuming members to be axially rigid. By assuming that, so here the kinematic independency will be 3. So you have to identify those kinematic independencies. So that is, I told you here, in rigid plane frame, at each joint you have possible 3 displacements at each joint, like this, 2 translations and 1 rotation at A and D. At A and D, since it is fixed, there are no possible displacements. There are no displacements which are possible because it is fixed end. All 3 displacements are 0. Then, since we are assuming members to be axially rigid, the vertical displacement at the ends are not possible. That means here vertical displacement is not possible. Here also it is not possible because this end is fixed, this end is fixed. If these 2 ends are allowed to move upwards or downwards, then this also should be moved there. But since that moment is not there, so the vertical motion is not there. And of course, rotations they are there. So that is, this is 1, this is 2. Then, as for the horizontal motion, that's also there. But since we are assuming members to be axially rigid, whatever motion at the left end which occurs, same thing will be there at the right end also. So the same displacements, it will be there, three coordinates. So there are 3 coordinates. So in the second step, wherein you are finding system coordinates. Second step is identifying the system coordinates. That is corresponding to these kinematic independencies. That is, I have already identified 3 coordinates. So, corresponding to these kinematic independencies, there will be 3 displacements. That is, 2 rotations corresponds to 1 and 2, and a sway or translation corresponding to 3rd coordinate. So these are 3. And corresponding to these system coordinates, what is the load? Because the system coordinates are along the global direction or system direction, system coordinates. Whereas this one, it is along the element coordinates, local coordinate, global coordinates. So here, what is the load corresponding to global coordinates? That is, what are the loads corresponds to 1, 2, and 3. Right. Here, while determining the fixed moment, reactions here, this will be 25 into 6 by 2, that is also 75. Here also 75. W8 by 2, W8 by 2. Right? That also we have to consider. Because there is a coordinate here 3. Corresponding to that coordinate, I have to determine the load here. Here I am taking corresponding to only these element coordinates, that's only the moments. So that's why there at that time this I didn't bother. But now for finding the system coordinate loads, so there is a coordinate corresponding to translation also. So I have to determine a force here also equivalent member and force, and that will be 75. That is this whatever the reaction which is there due to these moments that you have to determine. That will be, since it is symmetric, that will be half the total load. Total load will be 25 into 6, 150. Half that will be acting there in the opposite direction. That you have to take. That's it. so that of course you can reverse that direction. So here, this loads corresponding to PSR, loads corresponding to coordinate 1, that is nothing but here, this 2 and 3 sum, that is these two sum I have to find out. PM2 plus PM3, that will be the load corresponding to this. So that is 75 minus 75, so that is 0. Next, load corresponding to 2, that is load corresponds to 4 and 5. 4 and 5, that is 75. 75, yes, that's the total load. And then load corresponding to 3, it is 75. And that load, I have to take it here. So those are the loadings. And this loading, I can reverse its sign because that equivalent current load to take it, and that is that. 75, 0 minus 75, and this. Next, third step. We have to find the unassembled stiffness matrix. So for that, I have to determine the stiffness matrix corresponding to each of the members with the element coordinates. So for member AB, that is 2EI by L. EI of the member AB is 2EI, so it is 2 into 2EI divided by L, length 6 meters into 2, 1, 1, 2. That is the element stiffness matrix. So that I have to remember, so that I am writing that. So this you can simplify as equal to 2EI by 3, 2, 1, 1, 2. Similarly, for member BC, it is same 2EI and same length 6. So I can straightaway write this is equal to KM BC. AB and BC, they are having same element stiffness matrix. Then you can take for CD, that is for this member, that is also 2EI by L. So 2 into EI is EI here. It is not 2EI, it is EI divided by L is 3 meters. 2EI by 3, 2, 1, 1, 2. So these are the stiffness matrices for member AB, BC and CD. All these members, stiffness matrices you arrange diagonally, you will get that unassembled stiffness matrix of the structure. Km is equal to this here 2EI by 3, 2EI by 3. So I can take that 2EI by 3 outside, 2EI by 3. I will get 2, 1, 1, 2 for member AB. And this is 0 for other two members. And for member BC, it is 2, 1, 1, 2, others 0. For member 3, that is also 2, 1, 2, 1, 1. So like this, diagonally, I am arranging this stiffness matrices along this leading diagonal. That is unassembled stiffness matrix for the entire structure. Then fourth step, we have to find what is known as displacement transformation matrix. Displacement transformation matrix that you have to generate. So these are each column of this matrix R you can generate by applying unit load along this global coordinate or system coordinate one at a time and find the corresponding displacements corresponding to element coordinates. So that is, I have to take that structure like this. Then I have to apply unit displacement along first kinematic independency direction u1 equals 1 and keeping the other displacements fixed. So d2, d3, I have to keep it 0, no displacement. Then successively I have to do it. Then I have to give unit displacement corresponding to 2. Then I have to give unit displacement corresponding to 3. Corresponding to 3 means it is translation, that is this. So I have to give here d3 is 1. So this will move like that. This also will move by same amount. So this is 1, this is 1. Here, if I give displacement like that, so that will displace like this. So this is a displacement given 1, 1. Similarly, here that I have given here is such. So this is that displacement. I have to try to calculate that, and with reference to that, that is the displacement given 1 proper square. So corresponding to each of these system coordinates, that is 1, 2, then 3. Corresponding to these unit displacements I have given. After giving that unit displacement successively, due to that displacement, I have to find out the element coordinate displacement. That is, I have to find the displacement here, 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 here. Same thing. Corresponding to element coordinates, whatever displacement which has occurred, that I have to evaluate. Here. So here, of course, naturally, I told I am giving displacement only along the coordinate, and all other displacements I am prescribing. I am making it fixed. So that means here no displacement, here no displacement, here no displacement, here no displacement. Only displacements corresponding to coordinate 2 and 3. Only that it is possible, that is equal to 1 in the clockwise direction, 1 in the clockwise direction. So the first column of that R matrix corresponding to 1, displacement is 0, corresponding to 2, it is 1, corresponding to 3, it is 1, corresponding to 4, 0, 5, it is 0, 6 also, it is 0. So that is the first column of that displacement transformation matrix. Same thing here, when I give unit displacement in the direction of second coordinate, here no displacement has occurred 0, here 0, here 0, here it is 1, here also it is 1, here it is 0. So the second column of that this transformation matrix will be corresponds to 1, 0, corresponds to 2, 0, corresponds to 3, 0, corresponds to 4, 1, 5, it is 1, corresponds to 6, it is 0. here. Here you have to be careful. So this is fixed here, here also it is fixed. Now see, this has moved, translation motion. It is not rotation, it is translation. Here it is rotation, here it is translation. So here I have to find out the rotatory motions. Rotation due to this translation. Here you have to be careful. Either to be here, no problem, because whatever rotation is there, you are taking. Here now, you have to find the rotations, that is slow. See, now this has moved like this. It has moved like this. So a moment is created like that. To oppose that motion, here there will be rotations in this direction. And that rotation with respect to vertical direction is nothing but whatever displacement is there, that divided by this height. That is the rotation. This is the rotation angle. So that angle will be 1 divided by height. That is tan theta. Tan theta is equal to whatever displacement is given, 1 divided by this. That is tan theta. I can take it as tan theta is equal to theta. That is the actual rotation which has taken place. And that rotation is tan theta, which is nothing but 1 divided by 6. So it is 1 by 6. Here also it is 1 by 6. Then here, this is the rotation. It is again 1 divided by this height. That height is 3. Here also direction is like this, anti-clockwise. The direction is very important. It is opposite to this. So this rotation also it is 1 by 3, 1 by 3. And there is no rotation here for this member. Simply it has moved. Suddenly there is no displacement or rotatory displacement. So it is 0 here, 0 here. So the third column here corresponding to 1, it is minus 1 by 6, corresponding to 2, minus 1 by 6, corresponding to 3, 0, 0, corresponding to 4 and 5 and 6, it is minus 1 by 3 and minus 2. This is important thing to remember. Here we are giving translatory motion. Due to that, rotatory motion I have to find out, because I have to find the displacement rotation here. So I have given the displacement, translated displacement. Due to that, what is the rotation which has occurred? That is nothing but tan theta approximately. And tan theta is that displacement which has given divided by that height. 1 by 6. Here it is 1 by 3. That I have taken. And that will be in the opposite direction than whatever displacement is given. So that you have to take. So if you remember that, so this also can be easily generated. Here, no problem, only whatever rotation is given, that's straight away we have taken. Here, due to rotation, translation, I have to work out what is the rotatory displacement. That's something you have to remember. So therefore, this rotation or transformation matrix for this is you assemble all these 0, 1, 1, 3 zeros, and here 3 zeros, 1, 1, 0, then minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1 by 3. So this is the displacement transformation matrix. It is A6 by 3 matrix. That's all. So in case of rigid plane, this is another thing which you have to remember. Slightly change. So then next fifth step, you have to find the system stiffness matrix. That is global or system stiffness matrix. system stiffness matrix Ks. So that by principle of contragradient, that Ks is given by RT Km into R. So we have generated R here, Km here in the earlier two steps. So we can generate this system stiffness matrix knowing the transformation matrix and resemble matrix. So therefore, this Ks is given by this RT is 0, 1, 1, 3 zeros, then 3 zeros, 1, 1, 0, then minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1. That is R transpose. Into Km, it is 2En by 3 into that 2, 1, 1, 2, others 0, 0, then 0, 0, 0, 0, 2, 1, 1, 2, then 0, 0, 0, 0, 2, 1, 1, 2. That is stiffness matrix Km. Then again R is 0, 1, 1, 3 zeros, 3 zeros, 1, 1, 0, then minus 1 by 6, minus 1 by 6, 0, 0, minus 1 by 3, minus 1 by 3. So this is RT into Km into R. So this is a 6 by 6 matrix. This is 6 by 3 matrix. So here column is equal to row. Resulting matrix will be a 6 by 3 matrix. So here this is a 3 by 6 matrix. Yes, 3 by 6 matrix. So this I have multiplied by this. So here again column is equal to row. So resulting matrix will be a 3 by 3 matrix. That is your AES. So if you perform this multiplication of matrices, you will get this AES, the 2EL by 3 into a 3 by 3 matrix I get. So I have the result. Straight away we will take it. So that Ks value you are going to get as, this of course after simplification I will get some common factors, I can take it out. So I will get here EL by 3 8 2 minus 1 because it is symmetric, then 8 minus 2, then 5 by 3. So this is that stiffness matrix I am going to get for global stiffness matrix after performing that multiplication. So then you can find out Ks inverse for finding the solution, or you can adopt the system also has linear simultaneous equation or finding this inverse which I evaluate that. So Ks inverse of course I don't have. So you can just solve it straight away either by linear equations without this case. Then last one step to find ds. That is, this I have to get ds. Then it as ds. That is d1, d2, d3. That I have to determine. That I am taking here. So for that I will use that force displacement relationship. So we have Ps is equal to Ks into ds. Force displacement relationship in system coordinates, that Ps is already you have generated, that is 0 minus 75, that is equal to Ks is EI by 3, 8, 2 minus 1, 2, 8 minus 2, minus 1 minus 2 by 3. And dx is what we are doing. d1 Now either you can solve this simultaneous equation or you can find the inversion of this Ks matrix multiplied by this, you will get d1, d2, d3. So solving, you will get d1, d2, d3 is given by 1 over bi into 17.65, 5.51, then 152.2. This is what you are going to get Ts value, D1, D2. So you have solved this. Then I have to find out this Pm into the number of forces. So if you determine that problem is solved, then last step, next step, you find Pm into the number. So that is analysis, finding the internal member forces as well as displacements at the joints which you are performing. So for finding Pm, you are using this equation. We have Pm is given by PMF plus PMF, that is the fixed member forces, and force due to this relation displacements, that is PMF plus Km into R into ds. ds you have generated here, solving is ds is nothing but d1, d2, d3 that you have generated, or you have already got, or is this, then Km you have here Km into R. So that multiplied by this displacement that you add into PMF matrix, you will get the member end forces. So the PMF is nothing but PM1, PM2, PM3, PM4, 5 and 6. PM6. All this. That is PM. That is PM is equal to PMF you have already generated, that is this minus 75, 75, minus 75, 75, 0, 0. That plus Km value, it is there, and R is there, and ds you have calculated, so you should take that Km, R and ds, then if you simplify, you will get the result straight away and give it here. You will get that value as minus 114 and 47.8, minus 47.8. So this will be the second coordinate, MBA. This is MBC. MBA plus MBC has to be 0. That automatically it is 0. That you can verify. That is a check for your result. Then you have 94.1 minus 94.1. This is also a check. MCB and MCD, that is corresponding to 4 and 5. Then lastly 97.8 weight 97 and 8. So this is your final member weight also. So that also you have to determine. What is that you have to determine during the analysis that you have already identified in earlier first step and second step that you are arriving at in the last two steps, sixth and seventh step, DS and TM, you are determining. After evaluating this KM matrix, this transformation matrix and KS matrix. All generation of matrices would be and performing matrix operations, addition, subtraction or multiplication, transpose, that you can do it. And with these matrix operations, we can analyze this structural problem. So this is the general procedure we follow. Any problem, we can take it and solve it. So with this transformation approach of the evaluating or analyzing, we get the film structure, trusses and beams. One problem I have and shown the procedure. Same 7 steps we have to follow and we can do any other problem. So with this, unit 4 is completed. Next we will take up the last unit, that is direct stiffness matrix. Today we just introduction to that direct stiffness matrix. Then I can analyze like this itself, beam, truss and frame problem. Thereby your syllabus will be completed.